Okay, so here we go. If I were to do this, hopefully you don't feel like an idiot and you're sitting there going, what is he doing? But if I were to do this and we were in the same space at the same time, hopefully what you would do back is this, right? So it's a wave. And I know it sounds silly, but that's what we're going to be talking about, real waves, physics waves. But the concept of this and then the response of this actually really says a lot about what a wave is. So here I am over here and I initiate an action. I do work over here. And then some distance away, someone else gets that signal and then does work over by them. And that's really what waves are all about. Waves are a mechanism of energy transport, right? So I do work over here, causing work to be done over there without me having to go physically from one thing to the other. Because normally, how, if we were standing a certain distance apart, could I do work over here and cause work to be done over there? Well, if I take my pen and I throw it at something, I've done work on the pen, I've sped the pen up, and then when it gets to you, it collides with you, and you do work on the pen, and the energy is transferred. So that's the big idea here. We're talking about mechanisms of energy transport. So I'm going to go now share my screen and we're going to look at some notes. Okay, let me get to the visualizer. There's too much in the way of it. There we go. All right. And so what we're talking about here are waves. And so I'm going to define a wave as a mechanism of energy transfer without the net transfer of mass or matter. Okay. And I know that word net there looks a little weird, and we're going to get back to it. Okay. Because I do want to contrast a wave with what I'll call a particle. Particle is a little bit of mass, right? For now, right? A discrete unit of something. Yes. When particles transfer energy, we get the transfer of energy through collisions. Okay. So if it transfers energy like a particle, it transfers energy through collisions. And when it transfers energy like a wave, there's no net transfer of mass from one place to the other. So another example here is I have my little slinky, yes? And if I do work over here, this hand, by moving up and down, you can see that that energy gets to my other hand. But any little bit of slinky matter doesn't actually travel from this hand here to that hand there. What travels is some sort of disturbance through the slinky. Okay? So that's what I mean by there's no net transfer of mass, that no matter actually travels from one hand to the other, but that signal does, and work gets done at my other hand. So what's the point of this video? Well, here we go, outlining our wave unit. So now that we know what a wave is or how to tell whether something is a wave or not, and we'll get a better way of doing that later on. What we're going to do first is we're going to categorize waves. So look at all the different types of waves and the way that we can categorize them. And the second thing we're going to do, not in this video, but in another video, is look at vocabulary to describe mathematically certain things about waves. And then another video, we're going to look at what we're going to call the properties of waves, which means what happens when waves interact with stuff. And the way that this unit works is we're going to build up complexity. So we're going to start with what we'll call one-dimensional waves. And it's going to be exactly this, a wave traveling through a slinky or a spring or a string. So the medium is one-dimensional. And then we're going to move up to waves in 2 dimensions, then waves in 3 dimensions. And it's going to be building up layers of complexity, except that as we're building up these layers of complexity, we're going to see that the same vocabulary repeats over and over and over again. So we want to have our vocabulary strong and solid at the one-dimensional before we move to the two and the three. Okay, so that's going to be the pattern. So now, What is a wave? It is a mechanism of energy transfer without the net transfer of mass or matter. We'll come back to some that word net again in a moment. So if I were to say, let's list some types of waves, stop the video for a second and brainstorm all different types of waves that you think about. Okay, now that you're back, here we go. And if you said some waves, hopefully, I mean, one of the most obvious types of waves that people come up with are water waves or ocean waves. So I'm going to put those here. Okay. We saw our waves in a slinky there. So I'll say slinky or spring waves. Not normal, but in physics, it's a very popular type of wave that we're going to see. So now hopefully another thing you heard of is someone said light waves. Now, when you say light waves, you probably mean something different than I mean when I say light waves. When you say light waves, you're probably talking about like light like this, which I would say are visible light waves. So visible light. Okay. And you'll notice I'm writing down my waves in a very specific type of pattern here. And once we get sort of like to the concept of visible light, you might think about, I don't know, radio waves. Okay. So stop the video now if you didn't think of waves like this, and think if you can figure out like, what am I doing here with these lists? What are other some types of waves and which list do you might think they might be on? So stop the video and take a think. All right, so let's list a couple more types of waves that you've thought of. Hopefully, well, we're not in California, so you might not have thought of these, but we have earthquake waves, seismic waves, and there are actually two types of seismic waves. I'm going to write them both down, P waves and S waves. Okay. And if you've ever lived through an earthquake and it's not been that severe an earthquake, you've probably experienced P waves. If you've ever lived through an earthquake that are S waves, they're terrifying. Okay. We'll get back to those later once we really know what the difference between those two types of waves are. You ever go to a sporting event and you think about, yep, that's right, the wave. I know it's silly, but we're going to think about that. So when we get back to it, we'll think about the wave, and it's that thing where everyone goes, yeah, let's stand up, sit down, and then it looks like the pattern moves around the stadium. Right over here, you might have thought of other types of waves like, I don't know, ultraviolet. And that's the last time I'll actually write the word ultraviolet. I'll write UV. Okay. You may have thought of microwaves. Okay. And then you may have thought of infrared waves, which are also called IR waves, which are also called heat waves. You might have thought about X-rays and gamma rays. And these are going to be all of the waves that we're going to be dealing with throughout the course of this course. So what's the logic of each of these lists? Well, it's pretty simple, actually. The stuff on the left feels a lot more physical, right? Tangible. And there's a reason for that. So I need to define another word before we can really get into what this is all about. And that word is medium. So what does the word medium mean? And no, I don't mean like someone who allows ghosts and spirits to speak through them. If you may have heard that type of medium if you watch too much Bravo. But no, medium. Actually, that's not terrible of an idea because that medium allows the dead to speak through them. In the same way, a medium for a wave is the stuff that a wave travels through. And for lack of a better word here, I am just going to use the word stuff, put in quotes, that a wave travels through. Okay. Um, and that doesn't feel very formal, but there's a reason why I want to say that, because that's a fundamental difference between these two lists. If you think about it, waterways require water to travel. Slinky waves require a slinky to travel. Seismic waves require the earth to travel. The wave requires people to travel. But when we start talking about visible light, right? Now, visible light can travel through stuff. It travels through the air all the time. If you look out your window, that is visible light coming through the glass. But visible light is able to go from our sun all the way to the earth. And what's between the earth and the sun? And the answer is nothing, like literally nothing, i.e., vacuum, right? Radio waves, microwaves, all of these types of waves can travel through vacuum. These types of waves cannot. So I'm going to come down here where I said medium, and we're going to have two types of media. We're going to have material media, and this is a medium made of matter, and a non-material medium. Can you still see that? Yeah. Also known as vacuum. I'm going to move that up for us there, right? Which is, of course, the absence, not of course, but should not say things like that. The absence, no, C, of matter. So what's the difference between these lists? Well, these types of waves require a material medium for transport. And we're going to call them mechanical waves. And the second can travel through a vacuum and material medium. Okay. And we're going to call these waves electromagnetic. And you might stop and go like, I knew that word electromagnetic because in chemistry, you'd have seen these all as our electromagnetic spectrum. We're going to get back to that. Okay. But yes, so can travel through vacuum and material medium. Although I will say that some of these electromagnetic waves can't travel through all material medium. For example, X-rays. When you go to the dentist and they take X-rays, what do they do? Yep, they put the big lead bib on you and those x-rays can't travel through that lead. I have a wall behind me. Visible light is not shining from Miss Marcini's office into my office. So not all types of electromagnetic waves can travel through all material media, but they can travel through some. But the most important thing is can travel through a vacuum, cannot travel through a vacuum. And so that becomes our distinction between these types of waves. All waves are either electromagnetic or they are mechanical based on whether or not they can travel through a vacuum. Okay. There is a second way to categorize waves. And I'm going to use my Slinky to do this. This is a material medium, right? So I'm making a mechanical wave. If I want to send energy from this hand down to this hand, there's a couple of ways I could do it. The first way I can do it is by moving this hand forwards and back. And you can see the little like energy, little pulse move from this hand down to this hand. I keep saying this hand to this hand because right, left, it's all the perspective is really weird on this, and my dyslexic brain can't manage it. So, but if you do this, what you'll notice here is the energy is traveling this way down the medium, but any particle of the medium, what you'll notice is it vibrates forwards and backwards, but every time it's done, the particle goes back to its original position, meaning its net displacement is zero. These types of waves are what are known as longitudinal waves. Okay. And these are the particles of the medium vibrate along the same axis as the direction of energy transfer. Okay. Now, I'm going to define another vocabulary term here. The direction of energy transfer is also known as the direction of propagation, propagation, of the wave. No, propagation. Propagation of the wave. I write this word so often, I never remember how to spell it. Direction of propagation of the wave. So the direction the wave propagates is the same thing as the direction the energy transfers. And that's a longitudinal wave. It should be noticed that per cycle, the net displacement of any point on the medium is zero. Okay, they vibrate back and forth. So I'm going to show that in a different way. Here we go. I've got my longitudinal wave here, right? And so you can kind of see this thing is making like little compressions, and the compression is traveling down like that, right? But if I were to look at any given one of these lines, they just move back and forth. I have another one here that might make this easier. No, don't need this, right? There you go. So if you look at the pulse, seems to be traveling down the medium, but any point on the medium is just going to be vibrating back and forth, longitudinal waves. Okay, so there you go. Our examples. I will have links to all of these sites up on Google Classroom, but there it is. So our example here of longitudinal wave, because if I try and draw the picture, it's going to be just a terror here. Okay. Sound is a longitudinal wave, right? Air particles of sound are vibrating back and forth, but when I talk, I'm not like expelling air that gets to your ear. It just vibrates the particles of the air. The reason why we had to differentiate the types of seismic waves, P waves are longitudinal waves. So P waves vibrate the earth back and forth from the epicenter of the earthquake. So there you go. Sound and P waves are our examples of longitudinal wave. You'll note that I didn't talk about slinky waves because we're going to find out that I can make every type of wave with a slinky wave. So it's not a good example of a longitudinal wave. All right, moving on. Another way I can make a wave is rather than move my hand forwards and back, I can move my hand from side to side. Okay. This is so much more impressive with my big long slinky in the classroom that is several meters long. Okay. But if I move my hand like up and down, you'll see a little like hill, whoops, a little hill make it to this other hand, right? And so here any given particle in the medium is vibrating also up and down, i.e., it is vibrating perpendicular to the direction of energy transfer. Because I can also move up and down. It's hard to see here, but once again, I get a wave that travels from one side to the other. So here we're going to have something that's known as a transverse wave. And here, the particles of the medium vibrate perpendicularly to the direction of energy transfer. Okay, so that's what's true about a transverse wave, or vibrate perpendicular to the direction of propagation. Per cycle, once again, the net displacement of any bit of matter of a point on the medium is still zero. It vibrates out, back, right, every time the wave goes through. And that's also what I was talking about, where the net transfer of mass is zero, because every particle is sort of like vibrating about a point, right? Or from a point and back to that point. So there's a transverse wave. The interesting thing about transverse waves, very big difference from longitudinal wave, is longitudinal wave, there's only one way to make it. Transverse, I could go like this, I could go like that. I can go actually at any angle because how many ways are there to be perpendicular to a line? And there are an infinite number of ways. So we're going to say that these have an infinite number of axes or planes along which the particles can vibrate perpendicular to the direction of energy transfer. And I'm going to give a different name to that, right? The number of the axes along which the particles vibrate, that section is also called a plane or axis of polarization. Okay? So we say that transverse wave can have an infinite number of planes of polarization. Longitudinal waves only have one plane of polarization, and that is the axis that is parallel and anti-parallel, so along the direction of energy transfer, right? But these have an infinite number of planes of polarization, okay? And so what are our examples there? All right, so thinking back to our lists, this is where I want you to think about the wave. It's not a real wave, right? It's just a good idea. Think about each person. Each person stands up, sits down, but the energy, the pattern is passing through them around the stadium. The net displacement of each person, if you're doing the wave right, is zero. You stand up, you sit down. It's a good mechanical model. Kind of silly, but it's a mechanical model. It's very tempting to think that water waves are transverse because you think about when you're in the ocean, you think about bobbing up and down. It's actually not true. We'll get back to it in a second, right? It turns out that all electromagnetic waves are, oops, all electromagnetic waves are transverse. Now, you might be saying to yourself, hold on a second there. You said transverse waves are the particles of the medium vibrate perpendicular direction of energy transfer. And you said electromagnetic waves can travel through a vacuum. There are no particles of that medium. That's a contradiction. And that's an important fact because we're going to become much more expansive in our idea of, for lack of a better word, what's wiggling? Like what can wiggle in a vacuum? And the answer is something can. And the hint is in the name for it. And we're going to come back to that a lot later. So, let me show you some transverse waves. So there we go. Yes, I will click to continue. Okay. No. There we go. Okay. You can see the wave energy traveling to the side, right? The wave energy traveling to the side, but any particle in the medium is just vibrating up and down, back and forth. Okay. If you want to look at that here, transverse, okay, you can watch the wave energy travel to the side and then it goes up and down. Okay, great. There's one last type of wave that we can talk about, and it is what's called a circular or surface wave. Oh, I should mention, going back here, there's another word for longitudinal waves. These are called also compression waves. And that should make sense because we saw like the medium get scrunched there when the longitudinal wave was going through it temporarily. So circular or surface waves, this is very hard to describe, but I will say the particles of the medium move in circles as the energy travels through. And this one I will draw a picture of, but I want to show you what this looks like. Here you go. Let me change this to the surface wave. Okay. Trace the path there. So you can see each point on the medium is going through a little circle, and it looks like the transverse wave, but it certainly is not a transverse wave. Okay. So let me go back to here. There you go. So each point on the medium is traveling through a circle, right? So this point on the medium is going like this. This point on the medium is going like this, so that the energy can travel through like that. Okay. And so our examples of circular waves, these are our water waves. If you really think about it, when you're bobbing up in the ocean, you're not just bobbing up and down, but you are actually bobbing back, forward and back, and up and down. If another way to think about it, a circular wave is like a combination of doing a transverse wave and a longitudinal wave at the same time. You end up in a circle. The S waves are also Circular waves. And those earthquake waves are terrifying. Those are the ones where, if you talk to people, it doesn't just shake buildings, but it also causes the ripples in the pavement. I was in San Francisco during an earthquake, and I unfortunately got to see some S waves, and just watching the ground heave up and down as you're on it. Like pavement asphalt should not do that, but it does. So there you go. So circular waves, water waves, S waves. So all waves are transverse, longitudinal, or circular based on how the particles move relative to how the energy transfers. And all waves are either electromagnetic or mechanical. So therefore, I can categorize all waves with two words. So an S wave, for example, is a circular mechanical wave. A radio wave is an electromagnetic transverse wave. Two words to describe every type of wave. So that is the categorization of waves and the end of this particular video.